Sorry, I haven't worked with this before. Okay, good. So, good. I'll give a sort of a background on me and our firm. Our firm was formed out of and partnered with the Princeton Physics Department and supplies physics-inspired algorithms to hedge funds and other trading institutions based on very recent work in the high energy physics literature. And we provide transparent and robust version of AI, which is kind of you can think of as a continuum limit of neural networks. And the thing is, this formalism can also be derived from introducing multi-scale dynamics in PDs and SDs. So essentially, you're looking at something that captures nonlinearity just as effective as neural networks, but you have a full control over this model. So it's no longer a black box. And what today, and it can deal with non-stationarity as well. And what today we'll talk about is a very special toy model case where you have very good analytical control, where you use Lie groups to actually to constrain density functions used in options pricing. So what are the motivations? In physics, Sasha Polyakov had a dream in the 70s to characterize the dynamics of a system purely in terms of symmetry groups, without reference to a PD or SDE. This approach is very nice, it's time and price parameterization invariant, and it can even capture some dynamics that cannot be described by a PDE or SDE. And the motivations in finance include the fact that time and log price translation invariance are common assumptions in a lot of models. Self-similarity of price processes has been observed and known since the time of Mandelbrot, so it's pretty common. These are kind of the notations. And our philosophy today will be, we start with a Lie group, G, there's no PD or SD. We write down its Lie algebra, and then we write down the representation of the Lie algebra in price time space, so kind of what it's doing to price and time. And then we demand that our observables are invariant under the action of these representations. And symmetries can constrain a lot of observables. The only one we'll be interested in today are the density functions, which tell you the probability of price 1 and time 1 going to price 2 and time 2. And so what is a Lie group? Only thing we'll be concerned with is that a Lie group essentially is uniquely characterized by the failure or the extent to which the operators fail to commute. So these CABCs for all A, B, and C uniquely characterize the Lie group. So for instance, this is a Lie group. All of these are just abstract symbols. You're not supposed to know what they mean. However, if you identify them with these particular differential operators, you see that you reproduce these same commutation relations. And these generators actually are very intuitive in what they're doing. H is just shifting time back and forth. P is just shifting price. G is just rotating the time axis, and C and D essentially together constitute zooming in or zooming out of your price process, where time is zoomed in or out twice as fast as log price. So now we will impose that our density functions are invariant under each of these symmetries. So imposing log price and time translation invariance is simple. It just tells you that your density function is a function of the difference of the log price and the difference of the times rather than them individually. Then you can impose scale invariance to constrain your options price function up to arbitrary function of a cross ratio. Upon imposing boost symmetry, you get that arbitrary function is actually an exponential, and you end up getting something that looks quite similar to your Black-Scholes density function, except that your delta, you have this factor of delta, which is not half. In fact, to get delta exactly equal 1/2, you need to impose a much bigger, higher dimensional symmetry group, which is the higher spin group, which has a deep and mysterious connection to the absence of arbitrage that we won't go into. But even if you assume a PD with some kind of nonlinear deformation of Black-Scholes, you can show that exactly the extent to which this delta differs from half can be related very exactly to the extent of your nonlinearity in your PD. And this works for other kinds of nonlinearities as well. So moving beyond Black-Scholes, at times of crashes, you observe that sometimes that time and price scale uniformly. So Hurst exponent goes from its Black-Scholes value of half to 1. And then this corresponds to a very nice group, the 2D conformal group. And essentially, you play the same game all over again. You write down its representation in log price times space, and then you impose that your density function is invariant under this, and you end up getting a Cauchy distribution, which is not wholly unexpected for crashes. And playing the same game by breaking and preserving different combinations of symmetries, you can get a lot of different density functions. And in particular, we were able to reproduce some that Peter famously studied through stochastic time change processes, the normal inverse Gaussian, and others as well. And so that's essentially it. And you can introduce non-stationarity in this as well by breaking time translation invariance. and essentially constrain the dynamics. You get very nice Henkel functions if you do that. So yeah, that's all I'll talk about. Please reach out to me for questions.